full-time class today because, you know, it's just right before the holiday. That's one thing. Another thing is that I don't have like 1/3 of my class. So I cannot do too many things. So my plan today is to take care of a few issues that we couldn't finish yesterday. Okay? And that'll end chapter 5. So once you come back from your holiday, we start chapter 6. Okay? The reading guide is already up there. So let me just discuss a few things. One announcement I'd like to make is that there's a quiz. It's about 2 weeks from now, right? That's May 17. It covers chapter 3 and 5. So you have enough time, I think. Okay, just write it down somewhere. So the first topic I'd like to talk about is the R packages. So I showed you this package foreign, right? So that you can read data that has a different format. But this car package somehow betrayed us. It didn't work. Maybe just a temporary issue. I'm pretty sure they'll fix it pretty soon. But for a while, we have to find something else, some alternative. So I searched it a little bit. And I found out that there is an alternative package. And the name is sandwich. So let's open your R and let's install this package. Okay? So hopefully everything works today. And let me show you how to get the robust standard error. This simple one. And then I'm going to generate this error term, U, from normal random variable. Okay? And the variance of U in this model is fixed at 1. So we have a homoscedastic error, right? Variance of UI. So maybe it's easier if I put I everywhere. Doesn't depend on who this person is. Okay? So let me generate a few things. I first have to tell what is B ner, what is B1. So let's do that. Let's say, type it please. B ner is 0.5. B1 is 1.5. So somehow in this simulation, we know the truth. Okay? So that's one advantage of doing simulation. We can control everything. And the sample size is 200. You can change it if you want to. And we need data. We need data for Y, data for X. Let's generate X first. Do you remember that this function generates a normal random variable? Now we need n of them. And we save it into R, into X. So X gets so X is generated from a normal random variable, just a bunch of numbers, 200 numbers. Let's generate error, U, again from the normal random variable. You can change these distributions later. Now finally, Y gets beta ner plus beta 1 times X plus U, right? And then maybe you can make a plot. So when the error is homoscedastic, the data typically looks like that. The variability here is about the same as variability over here, right? So that's how we know. Now let's run a regression. And let's compare our estimate against truth. So it's kind of close enough, right? Now maybe not enough. It's close, but not exactly. So perhaps sample size of 200 does not really have enough information that allows us a very precise estimate. So there is some uncertainty, estimation error there, right? So what I'm talking about is a gap between my estimate beta 1 hat and the true beta 1. Now let's get the variance matrix. We know that the function is VC of V. So this is the variance of beta null hat. This is the variance of beta 1 hat. So let me save it to M, for example. Let's just call it VM, the variance matrix. And if you type diagonal of VM, you only take the diagonal terms. And if you take the square root, that's the standard error, right? And compare this against the default standard error in R. So this is the default in R. And this is the standard error we get from the VCOV function. Exactly the same, right? So I'll use the same function. Now, as I said before, this default, this function VCOV, calculate the homoscedastic only standard error. It's just simply assuming that errors have equal variance. Now, if we don't believe that, then we are going to use this sandwich package and a function there. So V COV-HC. This is the heteroscedastic robust variance matrix using this sandwich package. And let's compare it against the usual one. Do you see any big difference? So this one, the VCOV-HC, is the heteroscedastic robust standard error. This more complicated formula, and this is the simpler one, homoscedastic only standard error. So that's how I generated Y. Anyway, if you calculate these two variance matrix, robust and not, the numbers are about the same. Can you tell me why? Why we have almost the same estimates? Because the errors we have is homoscedastic, right? The first one is good under homoscedastic error or not, right? The second one is good only under the homoscedastic error, because the true error is homoscedastic. They produce about the same answer. Do you understand what I mean? Okay. Now let me give you a different error. So in this case, I generate error in a slightly different way. So one trick I can use is So in front of this IID error, I multiply a function of x so that for each error may have a different variance or standard deviations. Okay. Now let me generate my y again, and let me do plots. So now it looks different, right? The degree of errors, the variance of errors are increasing. So it's one example of a heteroscedastic errors. Now I run another regression and save it in B. And then let's compare these two functions, two estimates. So this is homoscedastic only variance estimate. And this is the heteroscedastic robust standard error. And right now, it's kind of very different, right? So because of this convention thing, let me actually calculate the standard error from these two functions. So that's the homoscedastic only standard error. And this is the heteroscedastic robust standard error. Now their estimates are quite different. It can be a lot more different, but still there are some gaps, right? Why is it so? Because the true error is heteroscedastic. The second one is good under any instances. The first one is good only under the homoscedastic error. So it failed to produce the right answer. So there's a few calculations I asked to try yesterday, and it is related to the Gauss-Markov theorem. It says that the least squares estimate is kind of best estimator for the linear regression among all the unbiased linear competitors. So let's see how much you prepared. So step one is do a few things together. The actual claim uses y. So one claim we like to show is this one, right? So subtracting y bar or not does not change anything. Do you know why? Have you tried? If you just multiply everything here and there, you can easily show it. Well, let me just you can do this, right? And y bar is a constant for this summation sign. So you can put it out. What happens to this summation? That disappears, right? So we only have the first term left. Minus y bar times g. So that shows the claim. Okay? Now this is the regression model, and we believe it. From this, we can show that where y bar is the sample mean of yi's, x bar is the sample mean of xi's, u bar is the sample mean of ui's. This is second claim. Why? So let's start from here. So let's just calculate the sample mean of yi. So that's y bar. What is it? Now if we trust this model, we can use the left-hand side of the model for y. Now you just apply summation to everywhere. Now what is this? 1 over n sum of beta null. Beta null is a constant, right? What is it? Beta null. Now we can take out beta 1 outside. What is left? X bar. And what is this? That's u bar, whatever that is. Okay? So this is true. So we see that our model implies this. But don't be confused. In the sample regression line where you have hats, we have a slightly different one, right? So this one and this one are kind of different equations, right? So here we use the estimated regression coefficient. Here we use the 2 regression coefficient. So that's the difference. But anyway, we have so the discussion so far is that if this is true, this has to be true, right? So we can use these 2 equations, and I'm going to subtract them side by side. Then I'm going to have, now beta null will be cancelled out, and beta 1 is a common term. So we have this relationship. So that's our step 2. Now step 3. Now in this term, yi minus y bar, I like to use this guy, okay? Is it okay? By 2. I just use this relationship. Now let's multiply this term over here, this term over there. And let me remind you that beta 1 is a constant, so we can put it out. Now take a look at this. This and this, they are the same thing, right? We just cancel it out. So we are almost done. The only trick is, remember the step 1. In the step 1 we had yi and y bar, but the same logic applies here. Whether you subtract u bar or not, it really doesn't matter. Okay? It does not change a thing. So that's our step 3. Now, the first claim is, I'm going to show that beta hat is an unbiased estimate. So how to show it? Beta 1 hat can be decomposed into this way, right? And beta 1 is a constant. So you just put it out of expectation. To show this, we have to convince ourselves the second term must disappear. It has to be 0, right? The question is how. And yesterday, I told you that the trick is always the same, the law of iterative expectation. So this single expectation is equal to expected value of a conditional expectation, right? So that's the law of expected value. And you know, the one thing is that when we take this conditional expectation, we like the condition on all the x's, not just one x. Okay, but still true. So you can condition on 2 random variables, 3 random variables or more. The law still applies. So let's take a look at this guy. So what I mean by the conditional expectation is this is what I meant. By taking conditional mean given all the x's. So this is the law of iterative expectation. So it can be just single x or many x's. Now let's think about this. Let's think about this inside of expectation, inner expectation. You'd ask, what is the average value of this thing if you know the value of x1, x2, x3, and xn? If you know all the x's, what is the mean of this quantity? Okay, that's the question. Now, if you know every axis, this xi is a constant, right? There's no randomness. How about x bar? It's just average of all those xi's is a constant. So everything in the denominator is a constant, conditioned on this. And everything in the numerator except ui is a constant, so you can just pull them out, right? So all of these goes out, everything goes out, except UI, because we do not know the value of UI. Okay, so we still have to apply the expectation. Now what is last is, what is expected value of UI given that you know the value of x1, x2, x3, and everything? It has to be 0. Can you tell me why? The assumption says this is 0, right? So the mean of UI, if you know the value of xi, must be 0. And this guy asks, what is the mean of UI if you know x1, x2, xi, and everything? Don't you think that that has to be 0 too? So I wish I have something better. But let me try this. Okay, so listen carefully. Suppose that you're teaching something to a kid. Okay, he's in elementary school. You're teaching a trick, some kind of game, and he can do the game, he can play the game, if he knows how to add 2 numbers. Okay, so he can do it as long as he knows addition. So in that sense, knowing addition is kind of sufficient. Now suppose that there's another kid, and this kid knows how to add numbers, but he also knows how to subtract numbers, multiply and divide numbers. He knows a lot more. Do you think that the second kid can play the game too? What do you think? So the first kid only knows just one thing, adding 2 numbers. The second one knows addition, subtraction, and many more. Anything that the first kid can do, the second kid must be able to do it first. Do first, right? Do 2, sorry. So that's something like this. If you know the value of xi, you can calculate the expected value of ui. That's 0. Now here, you know a lot more, including xi. Now it's the mean of ui. It has to be 0. I hope it makes sense. Anyway, this is 0, so everything disappears. So this shows this claim. Beta 1 hat is unbiased. By the way, in your note, I have some error showing that the beta null hat is unbiased. To do so, you have to use it. Okay, so at least we know that the least squares estimator is unbiased. And the next claim is it is a linear estimator, linear in y. So the remaining question is, what is this wi weight? So we basically use the same trick. Just from the definition, right? And in step 1, we agreed that whether it's subject or not, it really does not change anything, right? Because of step 1. You gotta listen carefully. This is kind of tricky. Think about this. Can I rewrite the whole thing in this way? Do you think that they are the same thing? What do you think? Now write down a simple case when n is equal to 2. Okay, don't use the summation sign. Just use x1 minus x bar y1 plus x2 minus x bar times y2. Do the same thing for the denominator and convince yourself that this is actually the case. Why don't you write it down? To simplify things, assume that n is equal to 2. Okay? Don't use the summation and rewrite this expression. What I ask you to do is to rewrite this expression in a very simple case when n is equal to 2. That's what it means, right? And n is equal to 2. So if you rewrite the whole thing in a slightly different way, so this is W1 and this is W2. So actually kind of, it's not showing anything. It shows that the beta 1 hat is a weighted mean of your dependent variable. So you take your y, you take the mean, but with different weights. The weight depends on your axis. By the way, it has to be 1. Okay? If your x is far from the center, you give more weight. If x is close, you give less weight. That's beta 1 hat. Okay? But anyway, that's the claim in the Gauss-Markov. So at least we didn't show that the least squares estimate has the smallest variance. It's kind of more challenging. But at least we know that the least squares estimator is unbiased estimator, and also it's a linear independent variable. Okay, do you have any questions? Is it okay? I'll see you after the holiday then. So basically that ends chapter 5. Once you come back, we begin chapter 6.